For problem 1, we have power core loss and secondary power core loss. So we need to find the hysteresis and eddy at 50 Hz. Inputting 30 Hz at this formula, so we get our equation 1. A is equal to 30 minus 900 B over 30. Inputting 50 Hz at this formula, so we have to substitute equation 1A to equation 2 and get the B is equal to 0.004 and A is equal to 0.88. So we get our hysteresis and eddy power losses. Problem 2. So we have here a given of hysteresis and eddy losses at frequency 50 Hz, and also we have 50 Hz and a value of flux, and find the PI total at 400 Hz. Solution: inputting the value needed for hysteresis, we get 46.2 watts, and for the eddy current we have 307.2 watts. And to get the iron losses, just add the value of hysteresis and eddy, so we get the answer. For problem 3, we have here a given of apparent power 20 kVA and a frequency of 50 Hz and 2000 volts over 200 volts. So for open circuit test and for short circuit test, we have here a values and find the efficiency maximum at power factor and the load percent. For P out, we have 16,000 watts and P in 1640 watts, and for the PCU we have here a open circuit test 120 is equal to x squared times 300, and square root of 4 is equal to 63.2%. At maximum efficiency we have 120 watts, and for PN we get to 40 watts, and for the power output we have here 10,112 watts and the PN is 10,352 watts. Efficiency is equal to 97.68%. Circuits that refers to high voltage side, so we have a circuit here, we have a value here, core resistance and magnetizing reactance. By getting the resistance, A squared times RE is equal to 10 times 333.33, we get the value of RE prime and the magnetizing reactance. For B, we have a circuit referred to low voltage side. We have a circuit here, and getting the R equivalent, we have R equivalent over A squared is equal to 0.03 ohms, and for B, at power factor 0.8, 20 times 0.8, we have 16 kilowatts. And for PN, we have the P out and the open circuit and short circuit power, which is 300 and 120. So we get our efficiency 97.4%, and we get also our X equivalent and core losses.
Given apparent power 50 kVA, and we have here open circuit test and short circuit test. We need to find the efficiency at full load and at half load at power factor 0.7, then the voltage regulation at power factor 0.7, lagging and leading. Then letter C is the terminal voltage of condition 1 and condition 2. So solution: at A, we have here full load P out is equal to 50 times 10 raised to the power of 3 times 0.7 is equal to 35 wattage. Then the PN is equal to 525 adding to 430 is equal to 955 watts. So the efficiency of full load is P out over PN times 100, so we have here 97.34%. Then at half load, we have PCU 0.5 squared times 525 is equal to 131.25 watts. Then the P iron losses is equal to 430 plus 131.25 is equal to 561.5 watts. Then the P out is 25 kilowatts times 0.7. We have here 17,500. Then calculating the efficiency at half load, 17,500 over 17,500 plus 5615 times 100, we get the 4B voltage regulation is equal to I squared full load, or the secondary current is equal to R secondary cosine theta plus minus reactance secondary sine theta over V squared times 100. So by getting the turns ratio, 3300 or 3300 over 415 is equal to 7.95. Then getting the primary and secondary current, we have 15.15 ampere for primary current, and secondary current we have 120.481 amperes. And to get the primary resistance is equal to power over I squared SC. So T is sub 2 times tau, so 15.3 squared is equal to 2.242 ohms. And for the secondary resistance, we have here R sub 1 over A squared, so 2.242 over 7.95 squared, so 0.035 ohms. And by getting the impedance, VSC over ISC is equal to 124 over 15.3 is equal to 8.185 ohms. And the secondary reactance is X sub 1 over A squared. Plugging in the value, we get the 0.128 ohms. And to get the value of imaginary or the reactance sub 1 is equal to Z sub 1 squared minus R sub 1 squared. Plugging in the value, 8.185 squared minus 2.242 squared, we get the reactance sub 1 is equal to 7.788 ohms. And for the condition 1, which is lagging, we have the here voltage regulation is equal to 120.481 times the 0.035 times 0.7 plus 0.128 times 0.714 over 415 times 100 is equal to 3.38%. And in secondary condition, where it is leading, so the voltage regulation is equal to 120.481. Voltage regulation is equal to 120.481 times 0.035 times 0.7 minus 0.128 times 0.714 over 415 times 100 is equal to negative 1.94%. And answering to C, so the voltage regulation is V squared minus V sub V sub 2 minus V sub 1 over V sub 2 times 100. So 3.38% is equal to 415 minus V sub 1 over 415. So the V sub 1 is equal to 401 volts. And by getting the voltage regulation using the negative 1.94%, we get the V1 is equal to 423 voltage.